Hello, everyone. First, I'd like to thank the organizer for inviting me. Very happy to be here and give this talk. So I'm Robert Magnier. I'm a postdoc researcher at INRIA Paris, working on shape analysis with some focus on medical imaging. And just before this, I was a PhD student also in Paris, working on essentially shape comparison and shape matching with, in a kind of a specific domain, which is called functional maps, called the spectral shape correspondence. So in this class is called a robust method for non-rigid spectral shape matching, which is kind of a very specific title if you're not very used to this domain. And it is a very specific domain. So the good thing is that you will have kind of a very broad overview of not everything that's been done, but like all the general ideas that are being developed in this domain. And I'll spend, hopefully, well, you get an understanding of the domain, but you will probably have some nice tools you will be able to use in your own research, at least I hope, especially coming from spectral methods and how to encode correspondences between shapes. So I'll have a very lengthy introduction to introduce all the domain, to justify why we're doing all this, and then I'll dive into the more recent research on correspondence. So let's try with some introduction. So I don't really have to introduce everything, but I'll still kind of do. Today I'll be talking about shape matching, so shapes, and shape analysis. So here I'm showing kind of a patchwork of all the different ways we could obtain, not all, but some different ways we could obtain shapes. Like on the top right, we get the scan the data set, so like scan of an indoor scene, which is composed of a lot of different objects of shapes. I mean, I'm not going to define shape per se, because let's just stick with the intuitive definition of shapes. On the middle top, we get like this real scan of a human from the default data set, which is like a bit noisy. It's a bit captured with RGBD camera, I think, or maybe just RGB, which is kind of some standard real data. But maybe some parts, but now I'm kind of seeing a lot in my postdoc, but we kind of go, sometimes ignore, is just the medical domain, where there's a lot of 3D acquisition devices. So for instance, here we have slices of an MRI of brain from the OASIS datasets. And obviously, like the brain is a 3D shape, and you could analyze it either just as a volume, MRI volume, or maybe you have isosurfaces or segmentation mask, and you might want to just do something and understand what's happening automatically. Finally, some like very standard data is the one on the bottom right, which is more graphics data, very clean triangular meshes. Here it's just animated data because it looks nicer here, but this is the data maybe most of you are used to work with. And we will kind of stick to simple triangular meshes during the talk, even though nothing will be really restricted to having triangular meshes, but yeah, I'll try to focus on this a bit later. So, okay, there's all these different modalities and like all these different shapes. And the first question we can ask is, like, what can we do with one shape? Again, I don't think I have to convince you too much or like talk too much about this. But if we're given just a single shape, there's a lot of things we are able to do, mostly coming from by discretizing things from like continuous geometry, so like discrete geometry. If you want, I guess, more details on this, you can check the last talk from today. I think it's going to be a very nice introduction to this. So typical tasks we can do, just some of them are like local feature extraction, curvature being probably the most useful or like the biggest one. But there's a lot of other things you could try to extract from just the local geometry of a shape. It could be like tangents, planes, and so on. Another thing you could do is like try to compare different points on the single shape. That would be, for instance, intrinsic distances, or like geodesic distances, or diffusion distances, or like any kind of distance. On the right, I'm showing some kind of like shape segmentation of RNA molecule, so which would amount essentially to doing like clustering on one shape. But you could do other things like shape animation or just deformation. I'm going to talk about deformation a lot in the following slides. But all these things, there's like this, what are these things? There's a big literature on this for like 30, maybe 40 years, which has mostly come from like differential geometry. And they are now very powerful. There's still a lot of research on this, and there's still a lot of improvement that could be made. But we have very, very powerful tools. And this kind of raises the question of like, now what can we do if I'm given multiple shapes? Now I have this nice collection of Joes, which are going to follow us for the rest of the talk. And very generally, what we want to do when we have multiple shapes is compare them. Doesn't mean anything. You might already see that it's very, very context dependent. But we just want to say something about the collection as a whole, maybe not individual shapes. It could be just about detecting local similarity or local differences. Maybe we just need to have landmarks or features. And more generally, if I have this collection, what I want is understanding, like, here's a morphological variation, like how the shapes vary within the collection. So these are prehistoric Joes from prehistorical humans. They all come from different species, and you might want just to understand which species is the closest to each other. But you can maybe already understand that this is very context dependent. For instance, here, there are some missing teeth. So having or not having a tooth is not really important. So that's a difference we don't care about. However, maybe the number of teeth is important. So this is kind of, it's almost the same thing, but you have to really care about what the underlying application is. And so everything ends up being very context dependent. It's not going to be like a generic, shape comparison pipeline, because it's always going to depend on what you want to do afterwards. So always have to keep this in mind. And what I'll try to show during the rest of this introduction is that shape matching is essentially crucial for everything that I'm talking about here. And maybe it's already obvious for you, or maybe not. I think it's not too obvious if you're not used to the field, because if you want to compare shapes, a natural thing to do is to do shape deformation. So to try, here I try to do it manually, but like to try to deform one shape into another. It's kind of the intuitive things we do when we're given like two shapes, try to kind of model one into the other, which gives us a notion of like, oh, that's where things are moving, that's where the difference actually lie. Usually it's inspired by like physics-based model like elasticity or like local rigidity. It ends up being like rather hard to tune. I mean, if it works very well. If it doesn't work, it's very hard if shapes are not aligned, if shapes are very different, if there's missing data. And if you, even more precisely, if you try to do some very naive deformation, you end up having like pair vertex displacement, so pair vertex gradient, which is something you kind of try to avoid when you do optimization on 3D, or you want to heavily regularize to have like smoother gradients. But another path to doing comparison is shape matching. A natural way to think about matching is just landmarks, if you don't know about shape matching. Or we call it shape correspondence shape matching. It's like, I'm just going to use each word independently, but it means the same thing. So the idea is just, I got a point on one shape, I can give a similar point on the other shape. I can do this for a second point. And even more generally, instead of doing like 1, 2, 3, 10 landmarks, I can just do one landmark per point on one shape, and I just go find the corresponding ones, which is essentially, we call it dense shape correspondence. So it's like dense landmarking, we're just landmarking everything. You can see that here it doesn't make a lot of sense. So like, where did some part of the teeth go when the teeth is missing? It's just like an example, but there's no perfect matching, obviously. This is way more abstract than deformation, because we're just talking about where a point will lie roughly in space. So it ends up being very more general, but usually it's way harder than just doing shape deformation. So maybe now that we're saying this, maybe some of you are thinking, oh, wait, why not just throw deep learning at it and just end the talk? I mean, you could, but it's not that easy. There's a very nice talk about learning on 3D data just after, so hopefully you will have a good introduction to like the limitations, but I'm just going to raise a few points. First, the thing is like, there's a lot of different modalities to represent 3D shapes. So I'm going to mostly display triangle meshes, but you could have point clouds, you could have voxels, but you could, I mean, yesterday we saw geometry from like Gaussian splattings. Maybe you can work right away with some Gaussian mixtures without having to go through reconstructing a triangular mesh. And that's all the kind of modalities we would like to be able to handle with a network. Maybe not the same, but at least different networks which should work at least similarly. And when we're trying to process data, we want to have some invariance or equivariance, which is either hard to learn or hard to build in the networks. Essentially two approaches, which is either you want the network to be by default invariant to translation and scale, or you just do data augmentation to make it learn that it has to be independent from this. A more like practical approach is that people will usually come, when we try to compare things in a collection, they come with a very small collection, like 10, 20, maybe 100 shapes. Like the Joes, I maybe have like 20 shapes, I think Jing knows, but yeah. It's like 20, there's 20 shapes. And it's very specialized. It's not like some generic, it doesn't come from like everywhere. It's a very unique kind of data. And we want something that's able to work right away on this. And training on 20 shapes is a bit tough if you just do the whole pipeline end to end. I mean, it would work if we had something like pre-training, which was working, and it's a very vast area of research because it's really not working right now to do pre-training on 3D. So you cannot just have a pre-trained network and fine-tune on your 20 shapes and everything is going to work well. And no, I'm not even talking about what kind of laws you would use, which is also not so obvious because, I mean, optimizing for deformation probably is obvious. Optimizing for matching doesn't really make sense. So what we will need to do is to find ways to create a framework so that the learning part becomes very easy. And that if we want to do a network, we want something that is feasible to learn. And maybe it's not going to generalize, but at least it's going to be more useful than having something handmade. But we cannot just throw a shape and just hope for the best, because probably it's not going to work with on a small collection and without pre-training. But maybe in 5 years, it's just, you can just throw deep learning at it, I don't know. So what the rest of our talk will be about will be essentially presenting some spectral tools to do shape analysis and then present functional maps. I mean, 1 and 2 will come together, but so spectral tools will be new ways to analyze a shape if you're not used to it. And functional maps is a compact way to represent this dense landmarking, so the correspondence between shapes, as a small matrix, as displayed here. And eventually, I'll go to how to compute functional maps and how learning-based approaches are now used to compute these functional maps. All right, so before going to spectral analysis, I'll go back to a bit to shape deformation, which is going to be a nice introduction to the whole field of spectral shape matching. So again, deformation is a very, very natural way to compare shapes. In the plot I showed before, all the jaws were obviously aligned, which is probably not a trivial thing to have this rigid alignment. So it is like the first basic deformation we kind of always do when we're given two shapes on 3D. If you try to visualize, if you try to analyze, you want things to be roughly aligned because this gives already a lot of information. But this rigid alignment, you could also extend it to something that's non-rigid, and there's a whole field of learning non-rigid deformations. Like here we have this nice elephant being deformed, which comes, I mean, it was mentioned on Monday morning also, this exact same example, which is usually, this one is using as rigid as possible energy to deform. But the deformation here is defined locally on the surface. So you want local rigidity, or you have local constraints on the surface in order to deform it. And it's like one side of the spectrum, and the other side of the spectrum, which I felt was meaningful to mention here because it's not really known, is a field of what we call volume deformation. And it mostly comes from medical imaging, where you essentially try to deform the whole volume and not just the shape. And you have a deformation usually displayed as a deformation on the grid. Usually it's used for MRI data, but with this deformation, it doesn't make sense. You know, the brain deforms like crazy. But the idea is that you can have a small vector field and just integrate along the vector field to follow the flow of the vector field to get the deformation. And it's used a lot in medical imaging for deformation. It's very heavy, but it works very well when shapes are already aligned, obviously. But these deformations are very nice because they are physics inspired. So on the left, it's elasticity. You see the shape as a small membrane, which is a bit rigid. On the right, it's fluid flow, so you follow some the fluid mechanics. And rigid alignment is in the middle because you can see it as surface deformation or volume deformation. It just depends on how you you like it. And what's nice with deformation is you have a local, usually a local control on the deformation, and you have an explicit effort. You minimize usually an energy, which gives you just, oh, that's like the amount of effort to go to one shape to another, which is a very nice measure of the difference between two shapes. So, okay, I kind of only did the good things about deformation, so why will I be talking about shape matching? Is essentially because shape matching is here already. So, again, instead of correspondences, we'll define correspondences instead of motion of points. And this will allow us to capture a broader class of deformation. But what's important to know is that, or to understand, is that matching kind of always comes with deformation. So, for instance, when we align these two shapes, it's probably aligned using some kind of ICP algorithm. And how ICP works is you compute, you compute correspondences, and then you compute the best rotation that aligns with the correspondences. So essentially, I have correspondences. I think I have a small video showing this. I have correspondences, and then I'm trying to find the best rotation that aligns with the correspondences. So I computed the rotation after getting matching. And it's kind of generally always the case for all deformation models. They have some data attachment term. You have to judge how much you fit the target shape. So you have to have some matching somewhere within the algorithm. So it's kind of a necessary thing to have. And which is why we are going to focus on trying to compute directly the matching, just on the matching part, because there's a lot of deformation models, and the goal here is not to give you an overview of all the ways to deform shapes, because there's like way too many for 1.5. And we'll just, I'll just present you some of the methods to compute this matching between shapes. So I'll do a very rough definition, not a perfect definition, to be honest. But it's enough to understand some of the issues of the problem and how we get to this functional map framework. So essentially, let's just define shape matching as like given two shapes with two sets of vertices. Let's just forget about different modalities. It's point clouds, it's triangular meshes. Maybe we can see Gaussian splattings as just the means. And we want to find an assignment T between the two, which produces good correspondences, good meaning, whatever good means in your domain. So it may be invertible, no area distortion, you can preserve geodesic distances. The thing is, this is not like, this is a combinatorial problem. Obviously, we have two discrete sets and we want to find assignment between two discrete sets. This really looks like good correspondences is kind of, also, depending on what you select, you can end up with, you can just use optimal transport to find this assignment. This is literally built to compute assignments between discrete sets, between sets at least. But this is a pretty hard problem, and we cannot just visit every possible assignment. So we have to find a smarter way, kind of a relaxed way to compute it. There's sets of methods which try to compute these things without going through like the frameworks that I'm going to present just after. Typically, you have, there's optimal transport. There's also, if you try to just preserve geodesic distances, so you want to find the mappings that preserve geodesic distances, you have the Gromov-Wasserstein framework, which is essentially, let's say, based on optimal transport to compute this, but it's very, very heavy to compute. Some people are trying to compute mapping that just are geometrically consistent, so like neighboring points are just mapped to neighboring points, and this ends up also with very complex but very interesting problems. But here we'll take a very different road, and we'll talk about something called functional maps. So if you want, you can just forget about the right part now, because I'm going to explain it. But essentially, let's say we are given two shapes, M and N, and we have an assignment or correspondences, a correspondence function. Now, if I'm given a function on the right, let's just see it as a coloring, like the L2 integrable function, but let's just say, I color my shape on the right, I can easily just transfer the color to the shape on the left. It's very easy. For every point on the left, I just look at where T is going, and I pull back the color. So I'm taking the pullback of the pointwise map. I call it FT because that's how we call it in the domain. Probably we should call it T star, but it's not. We're going to drop the notation, so no problem. And the important thing is like, FT is a linear operator. And a linear operator between two functional spaces, between very nice functional spaces, if I don't even want to go to details, I can say, we're in discrete shapes, so we have finite dimensional functional spaces. So FT is just like matrix. It's an n times m matrix. But it doesn't look like we actually did anything here. So we just have some slightly more complex object. OK, it's a linear map, but why does it actually help? Let's try to see what it looks like in a basis. So we have, again, this nice pair of draw. So I change mn to 1, 2, because I think it's a bit easier to follow. So we have these two shapes, and we have the correspondence function. Now we want to find what the functional map will look like in this basis. So in this basis, in what basis will we look? We look in the canonical basis. The canonical basis is essentially, let's just say, the Dirac basis, when we can just represent a function and a shape, but just the value at each vertex. And so a function is just like a sum of Dirac or a sum of hat functions, because we are on a triangle mesh here. So if we have Diracs on one shape, like 3 different Diracs, I have three Diracs on the right shape. Now, if I want to have the representation of the functional map written on the top right in the basis, and let's say I just focus on this like correspondence between these two Diracs. What it means is that when I transfer the function that's just a 1 on the vertex on the right, it just ends up on a function which is just a 1 on the red vertex on the left, which kind of means that at the line corresponding to the vertex on the left and the column corresponding to the vertex on the right, we have a 1, and everything else is a 0. The rest of the line is a 0. If we do this for the green Dirac, we obtain that's a 1 here, and we just fill the matrix. We just end up with a binary matrix where every line corresponds to a vertex on the left, and the only non-zero on every line is just the assignment. It's just the index of the vertex on the right. So we didn't do anything, essentially. We have a more complex representation of a pointwise map, which we could just like embed as a list. So now the trick is that we should try to, we should see that from a functional map here, we can easily recover the pointwise map. We just take the argmax, so we find the only non-zero element on each line. But let's say we're giving the functional map as just a black box. You don't know what it is, we just have a black box functional map. So if we have given any function, you can give it to the black box and it transfers the function. How do you recover the functional map? So obviously you can just take a Dirac and transfer it, and you'll get a Dirac. So that's very easy. But if you can do this by linearity, you can also just transfer random noise and end up with random noise, which feels like it's a bit too powerful for what we want to do. And there's maybe a way to kind of compress it. And I will try to show some like intuition on why it will work. It's kind of a novel way for me to present it, but I think it's a nice way to see it. So if we go back to our shapes and black box functional maps, and we have our Diracs, let's try to transfer this nice red function. We give the reverse function to the black box, and we obtain a second red function. We can do this for the green and for the blue. So individually, we transfer all this Dirac. But by linearity, we can just take the sum of the 3 and transfer the sum of the 3. And what's happening here is that with 3 functions, essentially everything within the triangle, the geodesic triangle, has a unique color. So we can like triangulate all the correspondence that's inside by just being able to transfer these 3 smooth functions. So maybe if we're able to just transfer smooth functions, we might be able to encode correspondences way more easily. And it's kind of the idea of like the first idea of functional map is to look at pullbacks, and the second one is to look as to transfer only smooth functions and not to care about being able to transfer random noise. And the issue is like, how do we select a basis of how do we do to only get smooth functions? If you were on the line or on the square, you would probably use the Fourier analysis, like the sine and cosine basis. But for shapes, it looks like we don't really have this, but in practice, we actually have this. We have the Laplacian eigenbasis, which, maybe on the square on the top, which is just intrinsic variable, which gives you intrinsic vibration modes of a surface, whatever the shape is. So it is, these are the eigenvectors of the Laplacian on the shape. So Laplacian being different on every shape, because they have different curvature, essentially. And if we're checking the eigenvectors on like this one jaw. For example, I have the example of 3 different eigenvectors. This gives you very smooth functions, and I have a smooth to non-smooth, so like low frequency to very high frequency basis of functions, which will allow me to just do like essentially low pass filtering on everything, because I don't care about high frequency, I don't care about being able to transfer white noise, I just want to have very smooth functions. So this Laplacian basis is nice, first because it's generalization of Fourier, so it's like a natural thing we would do on simple domains. So it's kind of a natural extension. Because it's a Laplacian, first we like it because it's like maybe the most useful tool in geometry processing. It's geometry aware, it's isometry invariant. If you rotate, scale, translate, it's going to give exactly the same function. And the basis is orthogonal, which is not necessary, but is going to be more useful for what we show after. But I'll come to it just in the next slide. And also, it's a basis, so I can just take any function and decompose it into a sum of the harmonics, and then I can just low pass and just like say, oh, I'm just taking the sum of the first like 50 harmonics, and I don't care about having, n basis functions. I just need to have like maybe 100. I think it's time at this point to just, for those who kind of know a bit functional map domain, to kind of talk about the misconception about functional map. That sometimes it's presented as if Laplacian was really necessary for everything that's coming next, or that came above. And it's really not the case. We really care about just having smooth functions. And there's been a lot of work about how to have some bases that looks good enough for us, which are low frequency to high frequencies. So for instance, if you have point clouds, we don't have really a Laplacian, so there's been work on surface approximation, where we build a graph and something that looks like a Laplacian. And we have a basis that looks like a Laplacian basis, but which isn't a Laplacian basis, but it's really not important. On the right, there's also work on elastic basis. So the idea is to see the object as an elastic material, and you can try, instead of looking at intrinsic variation modes, which is how wave would propagate on the surface, you can look at how the shape would displace in space, and you find extrinsic deformation modes, and you can kind of feel like, okay, if the shape was elastic, this would be probably how it would, like one of the interesting modes. But this is a deformation field on the surface, not a function, but you can just project it on the normal and you get a nice kind of smooth functions. But this basis is not orthogonal, but I mean, we don't really care, to be honest. Things are just easier when the basis is orthogonal, but it's really not important. And again, it's these two that don't specify, I mean, they kind of apply, the elastic basis kind of apply to triangular mesh, but you could have any kind of data. If we have something that looks like a Laplacian, and which is a smooth basis, like a wavelet basis on Gaussian splats, but well, you can have functional maps. It's really, or if you have volumes, you can do like stuff with volumes. It's really not built in. There's also been work on learning the basis from a shape. This is not working too well, to be honest. It's a very hard thing to do, to be given a surface and try to learn a basis. But there's been some work towards it, which are pretty interesting. I think now there's been more modern approaches just seek to take a basis and correct it into some kind of canonical basis. It works if you're just like working with humans. I say, oh, every human has roughly the same basis. You just have to have some small correction, and this has been some more recent advances. And another issue with Laplacian is that it doesn't scale well. I'm taking eigenvalue decomposition of large n times n matrix. This is a bit annoying. So there's a few solutions, like we can remesh the shape and just try to upsample, but then you have to be careful about how you upsample because there's no canonical way of upsampling things. Or instead of remeshing the shape, we can try to remesh the functions. The idea is that we're not even looking at the like hat basis or direct basis. We're right away looking at functions which are sum of small geodesic circles. And this kind of factorizes the Laplacian the eigenfunctions in a way that makes it like memory scalable. By the way, this was just a small side note on this. But okay, now that we have a basis, whatever basis we have, let's just say we have a basis. What does the functional map now look like on this nice basis? So I put the formula back, and let's say we want to express it in an orthonormal basis because it's going to be easier. How do we represent a linear operator in a basis? We just take the functional map of any of the base elements, and we want to find its decomposition. Because it's orthonormal, we just do inner product. So that's the formula of the functional map. given like the two bases. So it's a matrix of inner product, which is essentially the definition of a matrix product. So this is just a matrix product between two functional maps, two bases with the assignment put somewhere in the middle. And you end up with a small k by k matrix. K by k, so there's no mention of number of vertices originally in the shapes. But it looks like, again, we're losing something. Like we compressed this big binary n times n matrix into a k by k matrix, a real, so like this, in practice, like float numbers, it's not even like integers. And we have a like small way to encode it. It looks like we probably discarded a lot of interesting information. So I'll try to show a small illustration of how much we lose by just doing a texture transfer. So the idea is like, I have a source shape when I put some texture on it. And then I have ground truth correspondences, so I can transfer the texture to another shape, which is equivalent to saying like, oh, I have the functional map in the canonical basis. And okay, so transfer is perfect by definition because I didn't lose any information as we saw before. Now let's try to see in this truncated spectral basis how much we can transfer the functional map depending on the size. We can transfer the texture. So I'm not transferring the function, I'm actually approximating the pointwise map and then transferring with the pointwise map, which is way harder because just transferring the function doesn't mean we have good correspondences. And we can see that starting from 50, it starts to look decent, and at 200, it's roughly indistinguishable. So with 200, with a 200 times 200 basis, or even like 100 times 100, to be honest, for most applications, we have encoded correspondences between the two shapes. And this would give the same result if we had 5,000 points per shape or 5 million points per shapes. This is entirely agnostic to the amount of points in the shapes because it's all encoded in the basis. It's a bit of a trick because we still have to keep eigenvectors in memory, so it's not like you need some extra information, but it's still a compression of, and a nice compression because now we're working on a very nice domain, which is just real matrices. But it's not only real matrices, because you can see that it doesn't look like it's just a random k by k matrix. It has some structure, and we come to the end of this technical parts, not worry. And the functional map has several cool properties, and it has a kind of a unique structure first. You can see that it's nearly diagonal. So the idea is that for near isometric shapes, the matrix is going to be almost diagonal. What's happening is like for the same shape, you would get identity with plus or minus 1 at every point because eigenvectors are just defined up to a sign. But it's not the only thing that's happening. We also have that the matrix will usually be near orthogonal. Why? Because essentially if the underlying correspondences are area preserving. In a continuous sense, because in the discrete sense, it can be a bit tricky to define area preserving unless you just stick to the vertices. Then the functional map is orthogonal, which is significantly easier to work with. It's very easy to check if a matrix is almost orthogonal than to check if a pointwise map is near area preserving. And even worse for isometry, because how do you check if correspondence are conformal if you're going to vertex maps? This is actually insanely hard. But you just have to check if it nearly commutes with the Laplacian. I'm not going to go into details on how we get this. Yeah, I'm not going to go into details. So this is essentially the end of the technical part. I have one last slide for everyone that kind of fell asleep during the technical part because it's a very different view, so you can forget about everything before, and this maybe will be enough to understand everything that comes next. The idea is not to see functional map as something that's going to transfer function, but something that's going to just align the shapes. So the idea that when we're doing spectral shape analysis, we're just not using x, y, z coordinates. We're using what we call, or maybe what I call, because I'm not sure, maybe there's like eigenvalues when we say spectral coordinates, but let's say what I call spectral coordinates, which are essentially at every point is represented by the value of each basis element. So if we're on a canonical basis, it's only zeros except a 1, at the index of the vertex. But if we're on a spectral basis, it's a more complex vector. What's happening is that this is actually for Dirac, this is just a projection. Ex is just the projection of the Dirac into the basis. It's as much how much we can represent the elements at the basis. But let's just think that now instead of x, y, z, we have this k-dimensional embedding of the shape. Now what's happening is that the functional map C is just the best linear alignment between these two embeddings. So you kind of have to relate these to like rigid alignments, where instead of looking at rotations in R3, we're looking at linear projection in AK. But we also saw that we kind of always want to have area preserving or near area preserving correspondences. So we want near orthogonal matrices, and it's like really related to having just working in the space of rotation, we're working in the space of orthogonal matrices or near orthogonal matrices in AK. And usually it's going to be enough to understand everything that's happening with functional map to just think that we're just aligning another set of features. But it also gives you some other intuition of like, oh, if you just have subset of correspondences, you can still find the best linear alignment, just solving a linear system with less rows, but it's still very easy. Or if you have the functional map, so you can align the shape, and you can find the assignment by just doing nearest neighbor on k-dimensional spaces. And this is usually an easier way to see anything that's being presented regarding functional maps. So that's the end of the technical parts. So I think I can take either questions or we can have a break or both. Doesn't look like there's a question right now, so maybe, oh, yes?
As you just said, like for near asymmetric shapes, the alignment is linear in this embedding space.
Mm-hmm.
So basically, this means like for non-asymmetric shapes, it would be like a non-linear alignment in the embedding space.
Yeah.
And is there anything which tries to tackle this?
So I think it's for most shape, it's going to be a linear alignment on the full basis. Yeah. But it doesn't, on the truncated basis, it's just going to be the best linear alignment we can get. There hasn't been things on how you. I think I might have seen something that actually tries to do extra stuff, but I don't think there's really been work on trying to extend to nonlinear deformations of this spectral space. But it should be possible, I think.
Further, you said basically that when we have like three directs or smooth directs on the shape, you can basically find
triangulate in the middle.
Yeah. Basically for every point in the interior of the triangle, but like the functional map frameworks usually, when you computer matching, they don't really preserve this consistently, no?
No, they don't.
What's the intuition why it doesn't work?
To me, that's just because it's not because like the intuition given by the triangulation is not really right, to be honest. To me, that's mostly what's happening here. And in practice, to me, it's still a mystery of why sometimes this like locality thing breaks down entirely. Even when we check when I embedded the functional map here, sometimes there's like big discontinuities, which are a bit unclear why they're happening. I don't think here it's happening clearly, but sometimes there's big discontinuities. And I think there's an issue of the hard cut on the spectral basis. Usually, like the small differences between how much you can represent a Dirac on one function and on the other function is going to most essentially break down the algorithm, I think. And if you were really able to transfer geodesic disk of the same spread, probably you would be able to have nice to triangulate things in the middle. What's happening is that you're trying a big Dirac is propagated to like a small Dirac, but with also kind of small waves everywhere on the surface. Is not a nice geodesic disk, and I think this probably creates some noise. But I'm not like 100% sure of what's happening here. I think it's, I try to dive at some point into these problems, but it's really, I think it's built in the basis, essentially. It's mostly an issue with the Laplacian basis and correspondence between the two bases.
So you say also like an issue with approximation of the
Probably, yeah. And I think mostly on the bit. I think if you want to have a perfect functional map, probably you would need to have infinite lines because you want the exact entire decomposition. And because you're stopping it at some points, there's an issue of like, the more you move on the right, the more you crop the capacity the capacity to reproduce the functions. So probably maybe using like asymmetric functional map would be better, but for the purpose of the talk, I think it's easier to see like square functional maps. But I don't think it's the best way to go to compute them. So, well, I think maybe we can take a small break because it was a lot of info. Let's now go on with the talk. It's really the end of the technical part. I think everything that's going to follow will be rather easy. If you're, again, if you're a bit like troubled with everything that was presented before, just think we are aligning spectral coordinates of shapes instead of deforming them. So now I'm going to present a few, like essentially sets of algorithms in order to compute functional maps, because everything that was presented before was, oh, how we define this nice embedding of correspondences from this correspondence function. But now we kind of want to go the other way around. It's like compute this function because it's a nice space to work in, and then try to recover the correspondences. So originally, with the introduction of functional maps, so in 2012, the idea was that, oh, we're doing functional maps, so we just have to transfer functions. So we will do something I'll call like descriptor-guided functional maps. So the idea that, well, we'd find set of corresponding functions on two shapes, and we just find a functional map that aligns these functions. So we need to have, if we have a k by k functional map, we need at least k functions. And what does this function? So if you have landmarks, well, I mean, if you have landmarks, you could do a lot of things like deformations. But well, if you have landmarks, you can use them. If you have segmentations masks, you can use them also because it's really just a function. But generally, what people use are descriptors. Descriptors are just automatic functions which capture geodetic features on the surface. So there's like HKS, which is like heat canal signature, WKS, which is wave canal signature, which are built from the Laplacian, which captures some kind of augmented curvature, let's say, but mostly it captures curvature, because curvature would be a very good signal to preserve. There's also shot descriptors, which are looking at distribution of normals at every point, which are working well. But you could think about other things. So I think there's been some work, maybe not really exactly related to functional map, but there's been some work still on, oh, you could do renderings of your image, then use some pre-trained dyno, like any image processing features or deep learning features, and then you back project on the shape and you get some features. They are maybe not perfect, but they are probably decent enough to have a descriptor preservation. But if you do this, there's two issues. First is, well, you have to hope that the functions actually match, which is usually not happening. And you kind of never care about the structure of the functional map. So we want a functional map that's near isometrics, or which commutes with the Laplacian, or that's near orthogonal, and that's never enforced here in any ways. And one idea that came up, like with this original article and a following article, is that you could try to do what we call operator preservation. So here, I'm showing the Laplacian because I talked about it before of like, oh, we want the function map to commute with the Laplacian, which is nice. The idea is that if we have any operator that should act the same on each shape, we can use it as a constraint. So essentially, for the Laplacian, what it means is that, oh, if I take a function and the Laplacian of the function and then transfer it, it's the same as I first transfer it and then take the Laplacian. So we want the behavior to be the same on the functions. And we could have a lot of different operators on this. For instance, we could say, oh, we have a descriptor function, but I want like also to do each level set of the function. I want to be able to transfer it. So you could add extra descriptors. This can be also explained as an operator, like pointwise multiplication by the function. And there's like different whole sets of operators you could define that would help you guide the functional map. And this, instead of, before it was just a linear solve, this you could still solve with a linear solve because this is the right term still is linear, but the easiest idea is just to throw some convex optimization things at it. So BFGS usually works the best. But this is really the, let's say, the original pipeline. When you don't know anything about the shapes, I really don't know how much it's used in practice. I think when people are trying functional maps, they're usually trying this pipeline because it's implemented. You can just throw your shapes at it. But it's not really studied anymore. Probably there's like a lot of improvements that could be made, but it feels a bit like old now, although it's the only one that actually do things from scratch. I think the most known algorithm or most useful algorithm for synthetic or even real data is called the zoom out algorithm, which is essentially ICP. So if we go back to what ICP is just alternating between I have correspondences and I find the best rotation. Zoom out is I'm alternating between finding correspondences and the best linear alignment. And that's all, except that instead of just having a fixed basis, every step I increase the size of the basis, which gives you something like this. So it's strange because it kind of breaks down at the beginning, kind of related to the question. But then you kind of zoom out, you like zoom out on the functional map, and you kind of increase the capacity, and it's I'm not doing anything, it just linearly just does ICP, linearly, automatically, so it does ICP, and it refines the correspondences. So you have to start from somewhere, it's not like from scratch. So if you have aligned shapes, you just take like nearest neighbor, and it's usually enough. If you have like two landmarks, maybe you can start with something, or you can still start maybe with descriptor function or anything that is the output of what I presented just before. But this is essentially maybe the only algorithm you need to know. It's ICP, so it's like 5 lines of codes. It's very fast. You can put it on GPU. It's trivial. And it has something that it favors isometric maps. So we're not looking specifically at orthogonal functional maps as in ICP, but what we're doing here is actually pushing towards these orthogonal functional maps. So the idea is to see the zoom out problem just like the iterative closest point problem as just a big optimization problem when you do like coordinate descent. So it's going to be a bit more of a tough slide, like a heavy slide. So the zoom out algorithm is actually the cycle on the right. So we have C and pi, which is a pointwise map, and we just alternate between minimizing the two. If you try to define what the original problem is, what the energy that we're minimizing is, you end up with what's on the left, so the problem relaxation. That is that we start from energy on functional map themselves, which is, let's just say, something that pushes towards orthogonality. It's not like a hard constraint, it's just a soft constraint on pushing toward isometry. And then you relax the problem by introducing a pointwise map, and then you do alternate minimization. Once you do this, you are allowed to just modify the left energy. And you could add a lot of other, instead of just having this orthogonality thing, you could have descriptor preservation, you can have bijectivity and compute things in two directions. You could have, let me check what I have there else. There's conformality, but I don't think it works too well. But usually you just use bijectivity and maybe descriptor preservation if you have this, because if you have landmarks or if you have any signal on your shape, you would want to put it into zoom out, and this is actually the way to go, and it's almost as easy. It's slightly more involved, but it's okay. But one kind of energy we would want to add, which kind of was raised by the question, that sometimes things are not smooth when we do this linear alignment in the spectral space. So can we add like smoothness energy here? But the thing is, when we're working in the spectral domain, we're kind of forgetting about this local, we don't have local information anymore. It's kind of all built in the basis. We don't really know what's happening locally. This is more in the spatial domain that we're going to see it. So there was like follow-up paper where instead of doing this energy on just a functional map, we just add an extra smoothness term, and we just essentially adds things everywhere. It just adds an extra variable, and but it just adds an extra set of energy. So here you have at the end a huge set of energies you could minimize by just plug and play. But by default, you would probably just use original zoom out. It's just if you have additional constraints, you would probably try to check other things. So I'm not showing you, there's other very nice papers I'm not talking about here, which are, one that I really like is one where you just start from random functional map and build a tree trying to explore all the possible functional maps you have, and you just do branch and bound on this. But I don't think it's that easy to tune for yourself, so I think I'll just stick to the practical side. But essentially, these are all the only thing I want to talk about with how to compute functional map from scratch. But there's a few limitations. Maybe a lot of limitations from what I presented. So first, it really relies on these handcrafted descriptors. Usually all pipelines are on, if you don't have initialization, it's handcrafted descriptors. And typically here on the two dragons, I have what should be matching descriptors, and you can see that there's, if you try to enforce it too much, you're gonna have probably a lot of issues, and every pipeline is going to struggle. What I didn't talk about at all is partial shapes. Because most things break down, we don't really want area preservation because there's missing parts, so some area disappears. We don't want isometry because, again, there's disappearing parts. And that's a subset of literature on specifically designed for partial shapes. Because what's happening is that if I have exactly the same shape, but one is cut in half, the functional map is not going to be diagonal, but it's going to be slanted diagonal, because every eigenvector that only exists on the part that's missing is just going to be skipped. So you're going to go faster into like higher frequencies on the partial shape, and then you have to find exactly what this, essentially you try to find the angle of the diagonal and try to fit things here. But these algorithms, again, are not, they're like very nice pipelines, but in practice it's very hard to optimize for it. And there's still like, I think, a lot of work to do towards partial shape matching with functional maps. A final thing is that there's no data-driven adaptability. What I mean by this is, again, we are usually, practitioners will come to you with matching problems, where the idea is that, oh, I have this small collection of shape, very, very specialized, but you are just throwing some very generic curvature-based descriptors. And for complex shapes, there's very few chances that this is going to work. So we would like to have something that's a bit more adapted to the data, that can like fit with the data and train on the data, which is why I'm going to talk about how deep learning means spectral matching, which is a more recent line of works. Everything I presented before was essentially until I think the origin of the development until 2019. There has been more recent developments, but essentially between 2012 and 2019. And this essentially started in 2018. So it's kind of almost two separate line of works. So let's just find the first slide on what should the network learn. So like what the framework for learning. The idea will be that we're going to learn descriptors, or we're going to learn, let's just say for now, point features. We could try to be learning like a global code and probably do something with like generative modeling and try to find the correspondences, but I think it's easier to think that, oh, we're going to, at some point in the network, compute pointwise features. And then we use these pointwise features to compute correspondences with whatever pipeline, whatever loss we want. The challenges will be that there's going to be no obvious loss functions, or maybe we already see that, or there are maybe with what you presented, obvious loss functions. But by default, there's no obvious loss functions to compute matching. And what we really want is to be able to do unsupervised learning in a low data setting. I mean, the low data setting will essentially be what network we're going to use. And I'm not going to talk at all about what networks we're going to use, and I encourage you to go to the first talk this afternoon, which is going to talk about this. But we want to do unsupervised learning. So the general framework, if I rephrase it, is we have our jaws, we have some kind of feature extractor, we're going to throw independently the two shapes. Here I put the same line, but they're sent independently, and we're going to get pointwise features independently. And what do we want at the end is essentially this pointwise map. I represent them as matrices because it's just for consistency with what happens, but you could just see them as just lists. So the natural way how to get this pointwise these maps are essentially, you do essentially nearest neighbor query. But this is going to, I mean, you can already see that the gradient is not going to flow at the right places. It's way too restrictive. It's not a very good way to do. So probably a natural thing to think is like, I can do like soft nearest neighbor. So like some kernel, exponential minus a distance, or anything that looks like a good kernel. And we have this soft nearest neighbor, and then we can do any loss on this pi. So what kind of loss? It's, again, not too easy. Maybe we want something that's bijective. Maybe we want to transfer some signal, but what signal do we have if we just have shapes? I think one big issue when you do this is that, you have your point features, you're doing this essentially softmax, and then even if you had ground truth correspondences, then you're just solving a classification problem. You're just trying to classify, you do logistic regression on every point, so you want to find where it should lie exactly, and you have no neighborhood information. So maybe you could do, instead of just in the softmax, it's still gonna flow in the rest, but it has no information about neighborhood. Maybe I could do like an extra sum with geodesic distances, and it's possible, but it becomes awful, and you have to fit geodesic distances in GPU, which is probably not something you want to do. So the gradient here is still going to flow in a terrible way, because either you are at the right point or you are not at the right point. There's no, I'm close, I'm almost there. There's no information about this here, no geometric information at all. But maybe we can transform this kind of soft correspondence into a functional map and then do things. It kind of works, but there's still an issue somehow, and I believe it's because, again, of the gradient flow is not too good when you just have this. But because you compute a functional map, there's somewhere multiplication with eigenvectors which kind of force a gradient to be smooth, and the gradient should be smoother. But somehow when I did the experiments, it didn't work working from this. And I think the real breakthrough, what happened originally in 2018, and maybe there was a paper just before 2017, where the idea is still that, we're going to compute these pointwise features, and we're going to get a functional map. But maybe let's just not see this as having pointwise features, but as having shape descriptors. So instead of checking every line of the features, we check every column, and then we just do what I said before. We do the linear solve of functional maps, or linear solve with some regularization, because it's gonna work better. And what kind of loss we enforce on a functional map? So we want the functional map to be like orthogonal, and maybe we compute in two directions, and we want things to be, the functional map to be bijective. And I think this is 2018, so it was made with a kind of old feature extractor. Originally was kpconf, but if you use more modern networks, this is probably like one of the two baselines you have to check. And this work, if you have random data, like small set of data, probably like, I think from 50 shapes, you can just train a network. You can optimize a network. You're not going to try to predict on like a lot of new data, but essentially you can just optimize the network to predict good descriptors for your data. And this is going to work extremely well. It's going to be very fast. Like in a few hours, you're going to have your results. And yeah, I think it's like what you should keep in mind. This is a great idea. And putting a loss on the functional map is very useful, especially for the gradient flow. And even if differentiating through linear solver is not, maybe it doesn't feel like a great idea, it does work decently well as long as you kind of clip the values. But yeah, that's the most important baseline, I think, right now. But there was another idea of like, now we're seeing only the features as functions. So we're really seeing the geometric part. But maybe, this seeing every point as the output as pointwise features was maybe not such a bad idea. And we can maybe just put the two branches and compute first a functional map where we see the output as functions and a functional map where we saw the output as point features. And we want the two to match. And that's the only loss we add. And I think this is the second biggest baseline. There's a few variations you could add on everything that happens on the left, on the feature extractor and how you actually get the features. But everything that happens on the right is essentially just a new kind of loss. And the idea is just, we see the output as two different things. One is geometric, one is not geometric, and we want things to align. And this really improves the training. And whenever the alignment loss start to decrease, then everything works very well. Maybe it's important to note that everything that we're doing is just designing a good loss that has a good gradient. It's just about this. It's not about adding parameters. It's not about building something that's bigger, because everything on the right just drops at test time. This is just to design a good gradient for our network. So maybe if the feature extractor was just very, very smooth, only doing smooth functions, maybe you could have anything on the right and the gradient would be good enough. But that's not what's happening with our current pipelines. But in this pipeline, there's one thing that's a bit annoying is that, there is a linear solver, and we want to differentiate through the linear solver. And although I said, okay, if you're careful, it works well, but in practice, you can see sometimes that things are breaking down because if it's ill-conditioned with the output of your network, if your network starts to collapse a bit, then everything breaks down right away. So there was one line of work where we tried to replace the spectral branch entirely. And the idea that, we still output the pointwise features, and then we use zoom out. And in zoom out, we see both the features and the function. So we still use this as a geometric information somewhere because we're computing functional map from a very function-based perspective, let's say, well, even if originally we had just this similarity map. And zoom out outputs a refined version of the functional map. And what you can say is essentially, maybe the input, my original functional map and the output of the refinement should be the same, which is some kind of sub-supervision loss. And this worked decently well, but obviously because zoom out really wants something that really works for shapes that are near isometric, it pushes toward isometric maps. If your shapes are very, very different and very non-isometric, this is not going to work because zoom out will never work even with a good initialization. But this is essentially like one of the updates that was proposed. Another update that was more recently proposed is to add some deformation, because we kind of forgot about deformation all the way in the beginning, but they are kind of intertwined. And the idea is that, we can do whatever you want for computing the functional map, whatever block you had before, and then you feed this into an interpolator, which is essentially a network that's going to predict a deformation field from one surface to another. And then you can regularize stuff, and you can hope that if you enforce the deformed shape to be like close to each other, hopefully this will help the whole network. So I think it's a good idea. There's only one issue, is like you kind of expect to have aligned shapes. So either from the first functional map, you align the shapes and then feed this to the interpolator, or then you expect to have originally aligned shapes. But if you have aligned shape already, probably other things would work very well. Because on the pipeline before, nothing depended on the XYZ coordinates. So you kind of hope that things were doing well, whatever the data you had. Here you kind of expect aligned shapes. But if you're working with like medical data, usually you have aligned shapes. So sometimes it's not that much to ask to have shapes that are roughly aligned. So this is the end of the learning-based approaches. And I'm going to spend quite a lot of time on only one slide because these are the open challenges and limitations. And there's quite a lot of things to say about this. So first, the learning-based pipelines, or even the non-learning-based pipelines, they all rely on descriptors because they take the shapes as input. Networks take shapes as input, but they actually kind of take signals on the shape as input. Maybe they take XYZ, which is a signal on one shape, XYZ. And so there's a heavy reliance on this, which kind of shapes the whole solution. If you take XYZ, you kind of have to be careful about, if my shape is translated, rotated, scaled, everything is going to change. If you take descriptors, hit canvas signature, for instance, or this is independent from translation and rotation, but you have an issue of like, if you have a symmetric shape, the input is going to be symmetric. Hopefully the network will be able to distinguish between the two, but that's not always what's happening. And these are really shaping the solution, and I don't think there is right now a very good alternative to these very bad descriptors. And hopefully this will change in the next few years, but right now I think it's probably the biggest limitation. The second limitation is, again, partial matching, which is essentially often ignored because it's, I think, way too complex. Even earlier in the talk when I presented what shape matching is, I never talk about, I never really presented partial shape matching because this becomes, when there's missing data, everything becomes very hard to define. And there are some specific pipelines designed for partial shape matching, which are using essentially cross-attention between the descriptors, but these don't work too well in practice. It's still like an ongoing film with a lot of ongoing efforts to actually be able to work well with partial shape. I mean, it's still a bit hard with full shape, so with partial shape it's insanely hard because it's very easy to collapse into, if there's some data missing, I just say everything is missing and, I have a perfect score. So you have to regularize this, and it kind of looks like a GAN of like, I want you to ignore some parts, but not everything, and you have to find the right parameters, and it's very painful to work with. But in practice, that's kind of, whenever you have real shapes, you usually have partiality, and you really want to be able to go above this without having to pre-process everything to remove all the partiality. And I think it's also one of the biggest source of issues when you want to use in practical scenarios. A third point is evaluation. There's a paper this year about trying to evaluate shape matching method. I think this is also maybe, I think everything is a big issue, but this is pretty terrible because we are only essentially evaluating shape matching on shape matching with clean synthetic data. Usually, even if there's like cuts and holes, it's only like this kind of graphics data without any kind of more general scenarios. But the issue is like shape matching data, like ground truth correspondences are very hard to obtain and very expensive to obtain. So we kind of do with what we have. But I think there's maybe there's a philosophy problem of like we're focusing a lot on accuracy, on like being able to be very close to the tag, what point we should be, but never care about what we're going to use the network for. So if we have very good accuracy, it doesn't mean we're really robust or we're really useful for whatever applications we have below. Maybe we just care about having smooth correspondences rather than very precise correspondences in 95% of the case, and 5% that's like nowhere. So there's a trade-off to be taken into account, which is never evaluated for, because again, it's not easy. It's very easy to say, like I'm just saying it, but it's very hard to actually get data and get good evaluation data for this. And also, most of the case, the benchmarks have little variability. So we're working with human shapes or animals, but not even like man-made objects, or where they have big issues of topologies, and let alone just some complex medical data. And a final point is, again, generalization. As I said, you're usually using the network. You have the collection, you're just training the network on your collection, and you're expecting to have good correspondences in the collection. You don't, I mean, you can, but you don't really expect the network to work on new data. I mean, that's how we evaluate it, so we know it's still possible, but I don't think the capabilities are that good. Because, again, it's really dependent on the input descriptors, which are really shape-dependent, and it really has to adapt to the collection. So if you give a shape which essentially should have been in the collection but was not, it's going to work well. If you give something that's a bit different, the features are probably going to be very, very bad. So the generalization is essentially inexistent, and there's no pre-training strategies. I mean, not that there's no, it's like there are pre-training strategies that we just know they don't work, so there's no paper on like pre-training doesn't work, but essentially it's kind of a known thing in the domain that it's useless to try to pre-train your network. And I think that's most of the problems in this shape matching community. And I think that's all. I'm a bit early, I think, 14 minutes early, but if you have questions, I think it's the right moment. Yes?
Have people done implicit functions like matching?
I think, yeah. So this is a very different, essentially it's a very different domain, because we're kind of in implicit functions. Oh, the question was like, is there people working on matching implicit functions? So there is some work on it. I think usually people are mostly trying to deform the implicit function with the network, either with a vector field or just predicting a new implicit function. But I think usually it just deforms the implicit functions. And it's a bit tough to have any functional maps because there's no, you could do a basis on implicit functions. You could try to have some kind of adapted wavelet-based thing. If your function is, well, I'm thinking, no, I think if you have implicit function, you could probably have a basis. The issue is like if you cannot just open and close within the network, because then the basis will probably break. But it's pretty hard to have this. How to say it? During training, you cannot really compute the basis usually. So you need to have a very fast way of getting the basis in order to be able to have a differentiable loss that would work all the way. There is not even work on how to get a basis from implicit functions. I mean, I think there are multiple ways to do it, but one that would make sense is, well, which one would make sense, sorry, is not that obvious. But I don't think I've seen really things in practice, except when they actually explicitly rebuild the surface, then compute the basis, and then do the rest. But this feels like a very heavy step, and you're kind of missing out on the whole implicit thing when you try to go back to a surface. And I feel like there's mostly potential on trying to work right away with the kind of data we have. Kind of like I mentioned with Gaussian splatting, I think there's probably a good way to process them without having to go through the whole reconstruction process of a triangle mesh. But maybe not, but I feel like it's a more pleasant way to think about it. Sorry, I didn't answer too much, but there's just not that many work. Yeah.
Hi, thank you for your talk. I was wondering, how does this compare to methods from example, elastic shape analysis?
So when people are doing elastic, I mean, the kind of line of work I know from elastic shapes is usually working with the shape space and doing geodesic interpolation. And what happens usually that they expect to have the correspondences right away. So usually when I deform like the elephant, it's you have a source shape and the target shape has the exact same topology. So, or what it could be is like, oh, you have a shape with a different topology, but if you have one shape and correspondence to a second one, you can just transfer, like do triangle transfers. You have the same you can transfer your topology on the other mesh, but essentially you have the correspondences, and then you can do some elastic-based approach. So when I mentioned the smoothness energies in the zoom out, essentially smoothness energies are you add some deformation energies. So you could add some elastic energy or anything related to this line of work. But usually then I feel like kind of like for deformation, like the matching comes just before elastic, and there's very few work that I've tried to like cross the bridge between the two. I think it's two line of works that have for very long been like shape deformation and shape matching that have been like working in parallel without ever like a crossing between the two, especially for spectral shape analysis, where people were like, oh, we're using spectral shapes and functional maps. We're not going to go back to like X, Y, Z and deform a shape. And I think it's kind of a big issue because there's a lot to take from deformation-based approaches. So yeah, I think they're kind of complementary, and they should definitely use each other's work to just improve the results. Yep.
Thank you for the talk.
Thanks.
The shapes or the methods that you presented today they work nicely on kind of low resolution meshes, right?
Like I mean, let's see when we see them. I think these are like 400,000 vertices, maybe. But
The functional map framework work well.
I mean, it does. I mean, it doesn't scale well because there's this nearest neighbor, high-dimensional nearest neighbor thing. So in practice, because if you see things as linear alignment, usually you can kind of subsample points. And if you go to the GPU, I think 400,000 is a lot, but you can go easily to like 100,000. But you have to put everything on the GPU. I think a lot of pipelines were only built like on MATLAB for CPU, and there still needs to have. I mean, I've translated a lot of MATLAB code into Python, but there's still like a lot of effort to be done towards scalability. And GPU-based algorithms, because it's relying a lot on like having sparse matrices or a lot of CPU-based approaches, and I think GPUs are also a bit ignored, except on the learning part, but I think from a just shape processing part, yeah, these 100-dimensional nearest neighbor queries are not so good. But I feel like there could be a smarter way to actually get the correspondences just by transferring some functions, some lower dimensional functions, and trying to like find assignments. Kind of like when we do this RGB, I forgot when I put the RGB, but where did I put them? Yeah, like when I do this RGB thing, I could, like each vertex on the left has a unique RGB color, so maybe I just transfer this and I take the nearest RGB. I think I tried this previously, and it worked decently, so probably if you have a very dense shape, you should probably try to do this. There's some work on like dense dense mesh for function map for dense function map for dense meshes, but it's still like mostly CPU based. All right. Right. So thank you for your attention. And we can go.